Okay, we're going to go ahead and get started here. We're going to look at some problems in chapter 30. And so these are about the nucleus. So we've ended here on our last section. We've worked all the way down to the nucleus of the atom. And I will work on problems out of chapter 30. I don't understand what you're asking. We're working on problems. We're working on problems. Is that what you're asking? Okay, so we're going to work on these problems in chapter 30 here. All right, so the first one that we're going to look at is chapter 30, we'll start with number 2, okay? So chapter 30, number 2, and it says how many protons and how many neutrons are in, and it gives you a list of different atom or nuclei, okay? So this is chapter 30, number 2. I'm going to change that to white so it's a little easier to see. Okay, so the first one is helium-3. Okay, so we have to remember that the name of the element gives us the atomic number, okay? And that's the number of protons. Okay, so the atomic number tells you the number of protons. Then this number up here is the atomic mass number, or A, which gives you the number of protons plus the number of neutrons. So what that means I need to do is I just need to look up what the atomic number of helium is. And I happen to know that for helium, the atomic number is 2. So there's 2 protons, okay? And then if the atomic mass number is the number of protons plus the number of neutrons, then all I need to do is take 3 minus 2 to get 1 neutron. Okay, so that's pretty straightforward. Okay, so let's just do another one really quickly. Let's do, they've got radium-226. So radium-226, okay. Now, I don't remember exactly what the atomic number of radium is. I think it's 90, but I'll go look it up real quick. If you don't remember or you don't have, you know, that off the top of your head, you can go look it up in your, no, it's 88. You can go look it up in your appendix in your book. So radium's atomic number is 88. So that means there's 88 protons. Okay. Then if there's 88 protons, then the number of neutrons is 226 minus 88. That gives you the number of neutrons. And that's whatever that is. That'd be 8 and 3. So maybe 138 neutrons if I did my math right. Okay, so that's what you do. All right, so you just have to look up the periodic table to get the atomic number for whatever the element is, and then you take the difference between the atomic number and the atomic mass number to get the neutron number. Okay, so that's not too bad. All right. Now, the next one that we're going to look at is nuclear stability. So that's the next section. So let's just look at, number 7. Okay. So number 7, it says calculate in MeVs the total binding energy for the following nuclei and the binding energy per nucleon. All right, so the first one is hydrogen-3. Okay. Now, the way you do binding energy, if you don't remember, is you take the difference between the energy of all the parts minus the energy of the nucleus. Okay, so what that means is the binding energy is equal to the energy of the parts. So it's the atomic number times the mass of the proton, because that's how many protons there are. And then plus the neutron number times the mass of a neutron, because that's how many neutrons there are. So that's the energy of the parts. Okay, so that's the individual pieces, the number of protons plus the number of neutrons, okay? And then you subtract from that the mass of the actual nucleus. So when it's all together, and that's, you have to look all those up, okay? Then to get it in the units they want, you multiply all that by 931.49 MeVs per atomic mass unit, okay? So these units will be in U's, okay? So you need the mass of the proton and the mass of the neutron and the mass of the atom in U's, in atomic, in the unit mass for the atom. So in your book, in the back, there's an appendix, okay, that has all this information. So if you go in your book and you look at Appendix C, all right, it gives the atomic mass of the neutron in U's is 1.008665, and you need all those numbers, okay? You need all those numbers. Don't round off. U's. The mass of hydrogen, oh, that should be mass of neutron. Mass of hydrogen is 1.007825, okay? And then I can go down and look up the mass of the isotope. So if I go down under hydrogen, okay, and I find hydrogen 3, which is also called tritium, okay, it's that the hydrogen 3 is the mass number of hydrogen, tritium is 3.016049. So now it's just a math problem. Now it's just, I take my numbers, so the number of protons, Z is 1 for hydrogen times the mass of a proton, plus the number of neutrons is 2 times the mass of a neutron, minus the mass of the atom, which I look up. So now all I need to do is just plug in these numbers. So this goes here. Oh, I guess they're calling that the mass of a proton, excuse me. Mass of a proton. This, oops. Okay, so this goes here, this goes right there, and then that goes there, and it's just a math problem at that point, okay? Then you need to multiply, since these are all in U's, you need to multiply by 931.49 MeVs per U. The U's will cancel because you'll have U's over here in these masses. So they'll cancel with this one, and you're left with MeVs, and that's what the question asked for, okay? So you just multiply all that out. So that's pretty easy once you remember that. So it's nothing more complicated, but you have to be able to look up the mass of the atom. You don't know that off the top of your head. You have to look those up, and that's in Appendix C of your book. Okay. All right. Okay, so let's talk about radiation a little bit. So it's kind of like balancing chemical equations in chemistry. You have to keep track of your, oh, before I forget though, I forgot one part of this problem. When it asks for the binding energy per nucleon, you take whatever you get for B and you divide by the number of nucleons, which is the atomic mass number, okay? So the binding energy per nucleon is just B divided by A. So you take B divided by, in this case, I've got 3 nucleons, okay? Because I've got hydrogen 3. Okay, if you'll excuse me just a second. All right.
See the cat behind you. They're so cute.
Yeah, that's one of my cats. Yeah, that's Fizzy. There's another one over there on the other side too.
How many cats you have?
7.
I try to meow them. They
oh yeah.
7.
Yeah.
I
Yeah.
love cats.
Yeah, they're good. They're good
You have
keys.
7 of them.
Yeah. Yeah. That's a lot.
It's a lot of
Okay.
work also.
Yeah, it is. That's okay. That's all right. Okay, so when we talk about radiation, let's look at problem number 22. All right. It says oxygen 15 and iodine 131 are isotopes used in medical imaging. Oxygen 15 is a beta plus emitter. Iodine 131 is a beta minus emitter. What are the daughter nuclei of the two decays? All right. So oxygen 15 is here. So the first thing I have to do is look up the atomic number of oxygen. Okay, so if I go on my periodic table, I see the atomic number of oxygen is 8. So I'm going to write it down like that. Now, it's going to emit a beta particle. So I start out with an oxygen, and it's going to emit a beta plus. So beta plus is a positron. The top row here is about mass. The bottom row here is about charge. Okay, so I've got 8 or 15 nucleons, and I've got 8 positive charges. That's what that means. Betas are electrons. Betas are not nucleons, so their number on top is a 0. They don't change the nucleon number. Okay, they don't contribute to the atomic mass number. But beta plus is a +1 charge. So what that means is this particle is going to come out and it's going to leave behind the daughter nucleus, and that daughter nucleus has to add up. So what that means is if I've got 15 on the left-hand side on the top, I've got to add up to 15 on the right-hand side. So if I've got 0, then this one has to be 15, because 0 plus 15 gives me 15. If I've got +1 on the bottom and I need to add up to 8, then I'm going to have 7 on the bottom over here. Okay? So it's just that simple. Then I go look up what 7 is, and 7 I'm pretty sure is nitrogen. Okay? So I go look up number 7, and number 7 is in fact nitrogen. So this is the daughter nucleus. This is what comes out of the decay. Okay? All right, now iodine 131 is a beta minus emitter. So I'm going to look up iodine. Iodine on my chart, when I find it, is number 53. It's a beta minus emitter. So beta minus still has 0 contributing to the top number, but now it's got a -1 down here because it's an electron. This one is, the top one is a positron. This one is an electron. So the same thing has to be true though. The top row has to add up to 131. So I've already got 0, so that's got to be 131. The bottom row has to add up to 53. Well, I've got a -1. So if I need to add up to 53, that's got to be 54. Because 54 minus 1 is 53. So I look up what 54 is, and 54 is xenon. Okay. All right. Okay. We'll do another one. We'll do 23. 23 is an alpha particle, and it says spacecraft have been powered with energy from the alpha decay of plutonium-238. What is the daughter particle? Okay, so plutonium-238, I go look up the atomic number of plutonium, it's 94. Okay, I looked that up in my chart. Now, alpha particles are basically high energy helium nuclei. So helium is 2, and the atomic number is, or the atomic mass number is 4, because it's got 2 protons and 2 neutrons. An alpha particle does. Okay, so the same thing's going to be true over here. The top row has to add up to 238. So this is 234 on the top. The bottom row has add up to 92, or excuse me, 94. So this is 92. and 92 is uranium. Okay, so it's just simple addition once you know what the particle is, okay? And it'll tell you it's an alpha emitter, or it'll write down the alpha, or it'll put a beta plus or a beta minus or whatever. Okay. Now, the only other kind that we'll see in here, well, we'll see two other kinds. We'll see electron capture and we'll see gammas. Now, we'll do one of those, and those are in problem 24. So we're going to do 24 part. Oh, there's not one in 24. Let's do, I take that back. Let's do 25 because 25 has both. So we'll do 25. So 25 wants you to find the mother particle. So I don't know what I've got over here, but I know it gives me an alpha particle plus radium-224. Okay, so the first thing I do is I write a 2 and a 4 for the alpha. I go up and I go over and I look up what radium is, and radium is 88. So again, the top has to add up and the bottom. So the top, over on this side, I've got 4 plus 224. So this is 228. And I've got 88 plus 2. So this is 90. So that is thorium. So I just add up the top and I add up the bottom. Okay, like that. And then I look up what element it is. Okay. Now, B part is a beta decay, a beta minus. So we don't know what the mother nucleus is, but we know we get lead 207 and we get a beta minus, which is a -1. Oh, they call it E minus. I was calling it beta minus. It's the same thing. It's the same thing as beta minus. Some books call it with an E and some books call it with the letter beta. It's the same thing. Okay, so lead, I look up, lead is 82. Okay, so I add up the top, and that's 207. I add up the bottom, and that's 81. And I look it up, and 81 is tellurium, TL. Okay, all right. All right, so on this side, since they're both on the right-hand side, I just add them up. I don't have to do, if the -1, if I was looking for the daughter nucleus, then I would have to get something that added up to the thing on the left-hand side. But since I'm looking for the mother nucleus, I just add up the stuff on the right-hand side, and that tells me what I put on the left-hand side. Okay, all right. Now, here's the new one. Here is an electron capture. So with an electron capture, what happens is the electron is on the left-hand side because I'm going to capture it. So this is a -1 and a 0 again. Beryllium is element number 4. So that makes this. So this top adds up to 7. Bottom adds up to 3. And so 3 is lithium. So if it's an electron capture, that's different than a beta decay. So this is a beta decay up here. And it's beta minus decay. Electron capture means it shows up on the left-hand side because it has to be captured before you can make something new. Okay, a decay means I let go of something and I make something new on the right-hand side. All right. Now, the last one is a gamma. So I don't know what that is. This is nickel 60 plus a gamma. Now, gammas are probably really the easiest ones, okay, because gammas are light waves. So they don't have any charge and they don't have any mass. So they don't change what element it is. It's still the same element. It's still nickel 60. But what it does do is this was an excited nucleus. So we put a little star there to indicate that it was an excited nucleus, kind of like we had the excited atoms in the last chapter. and it needed to relax down and release some extra energy. So, ooh, that's terrible. So the excited nucleus releases the energy in the form of a gamma ray, but it doesn't change what the element is. Okay, so if it's gamma, you've still got the same element, you're just releasing some excess energy. All right. Okay, let's do another one. Okay, so let's look at half-life stuff. All right, so we can look at we'll look at 32. It says barium-133 has a half-life of 10 years. So T1/2 is 10.5 years. A sample begins with 100, that means a bunch of barium atoms. So the original number of barium atoms was 1 times 10 to the 10th barium, 133 atoms. Okay. And it says how many are left after 2 years or 20 years or 200 years. So the time in this part is 2 years. Okay. So if we know the half-life and we know the time, then we choose the formula that says the number left after a certain time is how many you start with times 1/2 to the time divided by the half-life power. Okay, so the power looks a little funky, okay, but it's just T divided by T1/2. Now, as long as T and the half-life are in the same units, you can leave them. You don't have to convert years into seconds. Since these are both in years, we can leave it in years, okay? So this is going to be the time that's passed is 2, the half-life is 10.5. So the way I would solve this is I would just take 1 times 10 to the 10th times 1/2 times whatever 2 divided by 10 to the, or 10.5 is, and put that in there. Okay, so you'd find that number first, and then take 1/2 to that power and multiply it by 1 times 10 to the 10th. Okay, so you do this part first, and then multiply it by the number you start with. Now, if I'm waiting on, if the next time is 20 years, the only thing that changes is my exponent. Okay, this is still 1 times 10 to the 10th, and this is still 1/2, but now my exponent is 20 divided by 10.5. Because now 20 years have passed, but I still have the same half-life. And if it's 200 years, it would be 200 divided by 10.5. Okay, it'd be 200 divided by 10.5 here. So you just put in, this is whatever time has passed. So this is the half-life. And then this is the amount of time that's passed. Okay. All right. And then this is the number you start with. So this is how many you started with originally. And then to find the number at whatever time, 200 years or 20 years or whatever. So it's pretty straightforward if you know the half-life, okay? Now, if you don't know the half-life, there's something called the decay constant. You guys are being wild this morning. Go on. There's something called the decay constant, tau. So sometimes you know the half-life and sometimes you know the decay constant. But you can convert to the half-life. If you know the decay constant, the half-life is just 0.693 times the decay constant. So sometimes they'll tell you the half-life and sometimes they'll tell you the decay constant in a problem. But that's, you just multiply by, it's the natural log of 2 is what it is, but you just multiply by 0.693. All right. All right. Let's do one more. Let's look at number 46. Okay, it says a 50 kilogram nuclear plant worker, so the mass of the person is 50 kilograms, is exposed to 20 millijoules of neutrons. And the neutrons have an RBE factor of 10. We'll need that in a minute. They want me to find the dose in sieverts. Now the sieverts is sometimes also called the effective dose. Okay, so the dose of a radiation exposure is just the amount of energy per kilogram. So the rads is just the energy per kilogram. Then the REMS is the effective dose, or rads, or sometimes grays is the MKS unit, and then REMS and sieverts are the units. These guys are seen more in medical applications. These ones are the MKS units. Okay, so a gray, the number of grays is the amount of joules per kilogram that's absorbed. So if I've got 20 millijoules, so 20 times 10 to the minus 3 joules, divided by a 50 kilogram worker, I can find the grays. Okay, then to get to sieverts is the relative biological effectiveness, and that depends on what particle it is, protons or neutrons or gamma rays or whatever, times the gray number. So once I have the number of grays, I multiply that by 10 because my relative biological effectiveness was 10. Okay, so if it asks for the absorbed dose, that's grays. So this is the effective dose. Absorbed dose is grays. Effective dose is sieverts and MKS. But it may also ask you for rads and REMS, which are medical units, and they're related to grays and sieverts because a rad is 1/100th of a gray. So if you just divide by 100 to get to rads and REMS. And a sievert, or a REM is 1/100th of a sievert. Okay, so, but these are the MKS units, the sievert and the gray. All right. Okay, so that's pretty much all the different types of problems that you'll see in this section. Okay, in the lectures that I'm going to put up from last spring, there'll be some more problems worked out, so you can look at those too. But this is one of each type of problem that you would see in this section. Okay, got any questions?
We're going to have an exam after Thanksgiving, right?
Yeah, after Thanksgiving, just on this stuff. Yeah, on the atomic stuff and the nuclear stuff. It'll be a little bit shorter than some of the other ones. Yeah, it'll go up the Tuesday after Thanksgiving.
Okay. Thank you so much.
You bet. All right. We'll see you later.
See ya.
Okay. Bye-bye.